So we're going to start with talking about what the word rational means, because if you look at the section titles, they both have to do with rational expressions. First one's just talking about them, and the second is talking about the products and quotients, meaning multiply and divide. So rational itself means divide, and if I think about it, it means a fraction bar of something over something else. And pretty much what we're going to be doing is a polynomial over a polynomial. Now, since some of you guys weren't terribly great on this on the test, I want to kind of explain. A polynomial is any poly or monomial. When I say a polynomial, I actually mean anything that could be a polynomial. So, or even a monomial. So the number 2 is a polynomial because it's just part of a polynomial, and it's intended to be that. It's the constant term of a polynomial, just like that's the linear term and that's the quadratic term. So anytime we're dividing stuff, it's going to be a rational expression. In fact, 2 over x is not a polynomial, but it is a rational expression, and that's where it falls in the category of these things that we examine. Expression means there's no equal sign, and that's important too. So we're talking about things like this, x squared over x squared plus 1. That is a rational expression, and it's one where I can't cancel. That's going to be kind of a big theme here. What I want you to see is that this is actually x times x over x squared plus 1 as a group, and that's the prime factorization of that, and none of the factors are in common. So there's no canceling or really called dividing going on. We deal with things like this. This is another example of this, where I have x squared plus x to the negative 2, because that's really x squared plus 1 over x squared. And what we're going to be doing is adding those as x to the 4th plus 1 all over x squared, and that's what's going to make it a rational expression. So that's what this chapter is kind of heading. One little thing I want to kind of indicate is, remember that we've got to factor before canceling. We're always going to factor before canceling. Here's an example of that. If I have x plus 3 over 2x plus 6, an algebra 1 mistake is to start slashing those and think no. We are going to factor before canceling. So x plus 3 over 2x plus 6 is really going to be x plus 3 over 2 times x plus 3. Now, the question I want to ask is what that's equal to. How do I simplify x plus 3 over 2 times x plus 3? Well, do you remember back when I asked you questions like, what's the square root of x squared? Or what's 6 divided by 1/2? Or what's the Pythagorean theorem? Questions that always have a trick to them. Something deeper, something greater than just saying the simple answer. Like 6 divided by 1/2 is actually 12. Like the Pythagorean theorem starts with talking about in a right triangle, and the square root of x squared is this absolute value of x, not just x. Those kind of things are very, very important. If I go back to this problem and I slash these, which is probably what you're used to, yes, I get 1/2. But I can't truly say that the left side and the right side are equal. I can't. Because the left side tells you something, once I kind of remove those slash marks, it tells you something that the right side does not. What did that tell you? Well, the left side is saying we have a number divided by 2 times that number, and the right side is saying we just have 1 over 2. Okay, that's not helping much. How about I put it this way? This will be 1/2 for any value of x. This will be 1/2 for almost any value of x. Your mind should be blown here. The left side is not truly equal to the right side. I know, it's like one of those things that we always, that didn't close. One of those things we tell you and then we say it's not really true. So we're gonna make it true right now. I'm actually gonna make this true. How am I gonna do that? Well, if I'm gonna truly make that left side equal to that right side, I need to add a statement. I need to say that x is not equal to -3, or x cannot be equal to -3. Now they are truly, truly equal. Congratulations. So 2 sides, and this is where I'm going to put something. 2 sides of an equal sign are not truly equal unless they are equal for all values of the variable. This is why the square root of x squared is not really equal to x for every x. So, I'm going to call this, well, I don't want to call it Layton's Law, but we'll just call it something else. We'll just box it in, and I'll think of a name later. Because it's not in your book, but this is kind of an important thing. Here's what your book does, though. And this is very clever. It's a way to sort of talk about the math. For this section, your book actually includes a disclaimer. It says, assume that any denominator is not equal to 0. Okay, so that takes all the fun out of it, but trust me, we're coming back to that concept in time. Number 1, I'm going to simplify, and that's going to be my directions here. Simplify, under assuming that any denominator is not equal to 0. And you'll see that in our directions when we do stuff such as quizzes or tests. 5x squared plus 4x minus 1 over 5x squared minus 10x minus 15. If I factor the numerator, which is the first step to doing this, it's a trinomial. It factors into two binomials. I get 5x minus 1 and x plus 1. And if I factor the denominator, I'm going to pull out a greatest common factor of 5 to get x squared minus 2x minus 3. Okay, how does that help? Well, if I factor that denominator further, rewriting the numerator, because I want you guys going step by step, I get 5 times x minus 3 times x plus 1. Check by foiling to make sure that you're correct. And at this point, what I would allow is the slight, ever so faint slash marks that cross those common factors. X plus 1 divided by x plus 1 it divides out, provided, of course, that x is not equal to negative 1. We already included that in the directions. And I'm going to leave it as 5x minus 1 over 5 times x minus 3. I'm going to leave that. Yes, I do want you to leave the denominator factored. Don't multiply it back. Let's just leave it. So, number 2. X squared minus y squared minus 4x and then plus 4y. And we're going to put that over x squared minus y squared plus 4x minus 4y. This is a factor by grouping, so what I'm going to quickly do is group some things. I'm going to group this and this, and then I'm going to group this and this. And I'm going to be careful in the numerator of that negative. Watch how I do this. X squared minus y squared minus, pulling out the negative, 4x minus 4y, and then the bottom becomes x squared minus y squared plus 4x minus 4y. This can be really confusing. I can't tell you how many people want to cancel stuff here, and you can't do it. You have this plus and minus things. They mess it all up. We have to factor. We have to continue to factor. I'm going to pull that apart as x minus y times x plus y minus 4 times x minus y. Hang on just a second. Okay, just checking by multiplying that we were good, and we are. If I were to multiply the negative 4 back in, I would get a positive 4 here. I'm good. Denominator. I'm going to pull out x minus y, x plus y from that difference of two squares, and then pull out a positive 4, and I get x minus y. I can't tell you how many people here will want to cancel stuff now, and you still can't do it because you still have a plus and a minus. So what I have to do is I have to take my tools up here. So I'm going to leave pin because I keep accessing them all the time. I'm going to put a giant parentheses around the top. And I'm going to look at this. And I'm going to look at... Actually, let me highlight it differently. Let's do this. Let's highlight this and this within this and this. And you see that they both have the x minus y in common. And that x minus y is going to get pulled out, reverse distributive property, as x minus y, leaving behind an x plus y minus 4. Denominator, same idea. I'm going to pull out the x minus y. And what I get is an x minus y times an x plus y plus 4. Now that is factored. How do I know that is factored? This is critically important. I know it's factored because I have invisible little dots in between there. No pluses and minuses, multiplies. And now, and only now, can I cancel these two common factors to get a simplified version of x plus y minus 4 over x plus y plus 4. And that is my final, assuming, of course, the denominator cannot be equal to 0. So, third example. G of x equals x squared minus 3x, plus 3x minus 4 over 2x cubed minus 18x. Okay, what I'm going to ask you to do for this is to A, find the domain. How do we do that? Well, since this chapter is about factoring and more factoring and everything's factoring, we're going to want to factor the numerator. X plus 4, x minus 1. Check it out. Yep, that works. Factor out the denominator. I'm going to pull out a 2x, which gives me x squared minus 9. Let's keep that going. X plus 4, x minus 1 over 2x, x minus 3, and then x plus 3. When I find the domain, I have one first rule of domains, something to review. Remember that we cannot or no divide by 0. The cardinal rule in mathematics. And the rule 2 for domain is no square root of a negative number. Well, we're dealing with this first one here. So what I have to do is I have to look and say, what are the values that are going to give me 0 in the denominator? Those values are 0, because don't forget about that one, and then plus or minus 3. So what I'm going to say is x cannot be equal to those. And I'm going to say all x such that x cannot be equal to those. And put that in set notation. And that's my domain. I'll put a little d in front to indicate that that's domain. Step B is actually, or part B is actually asking you to find the zeros. If you remember back from the terminology I want you to know for this class, zeros mean the same thing as roots, mean the same thing as x-intercepts. And what an x-intercept is it's the value when y is equal to 0. Well, there is no y in a function notation, but you guys know that the g of x acts like y. So what's going to make, and I'm going to sort of bring this down here, but what is going to make this, let's see if this works, there we go. What's going to make this be equal to 0? If I have g of x equals this, and I want this to be equal to 0, it's not going to be the denominator equaling 0, it's going to be the numerator equaling 0. So zeros, they occur when the numerator equals 0. So again, what's going to make the numerator equal to 0? Well, those values are negative 4 and positive 1. And I'm just going to stick those in set notation because that's how we express zeros of a function. Let's practice this again. F of x equals x plus 3 times x plus 2 over x plus 3. I'm going to leave this one factored. It already is factored. Let me fix that right side, but while I'm doing that, let me kind of talk about this. You should know something about this. If I look at that, I can cross the negative 3's out, or the x plus 3's, but my domain should still be all x such that x is not equal to negative 3, because x could never have been negative 3. My zeros, on the other hand, don't tell me that negative 3 is a 0. We just canceled it with the denominator. My zeros are only going to include negative 2. That can be confusing, but if you graph that in your graphing calculators, you start to get an idea when you do a t-chart that we actually can't have a 0 at negative 3. I'm going to write that down. There is no 0 at x equals negative 3 because x cannot be equal to negative 3. So we'll be done there.